Analysis of variance, or Anova for short. Analysis of variance attributes the variance in y either due to the regression, and any part of y not explained by the regression will be captured by the errors. So the framework for Anova is as follows. We have the total sum of squares, which represents the total variation in y. And here it is. It's either explained by the regression, which is quantified by the regression sum of squares, and anything not captured by the regression will be captured by the errors, which in turn is quantified by the sum of squares or the errors, or SSE. So now I'm going to show you a visual depiction of what we just discussed right here. And here it is. So suppose that this here is the actual value for y, and the blue line represents the regression. So therefore, any estimate produced by the regression would be denoted with a hat there. And finally, the average value for y is represented by the green dashed line over here. Now, of course, there would be a lot of observations, some above the mean, some below the mean, but for simplicity, I've left out all those observations, and I'm just looking at one observation, because that's all we need in order to quantify these variables. So here we go, ladies and gentlemen. Let the process begin. First of all, how do we quantify the total variation in y? Well, total variation implies how far did the actual observation of y deviate from its mean. So that's what total variation is, total sum of squares. It's the difference between yi and mean of y. Now, the trick then is to take this total variation and break it down into the part that was captured by the regression, and the part that wasn't caught by the regression would be considered as error. So here we go. If the total variation was from here to there, this part was captured by the regression. So that this here, see that? Captures the part of the variation that's explained by the regression, and we quantify that with regression sum of squares. Therefore, the remaining part over here is the part that's not explained by the regression, and that would be attributed to the errors. That's all there is to it, ladies and gentlemen. That is it. So now what we're going to do is we're going to construct a table that builds off this simple framework. Here we go. So this is your famous Anova table. So first we look at the source of variance. And the way I got it set up is here's the regression, here's the error, here's the total. So we can look at it starting from the actually bottom. You could say, well, here's the total variation. It's either explained by the regression, or anything not explained by the regression is explained by the errors or captured by the errors. So then how do we quantify the total variation? Well, as I showed you here, the total variation is how far did the actual observation of y deviate from the mean of y. So it's yi minus y bar. And there it is, right there. Now that represents just one observation. So you gotta add up the dispersion for all observations. Now what's the square for? Well, you know, if you look at deviations around the mean, some will be above the mean, some will be below the mean. In other words, you'll have positive residuals and negative residuals. And if you just add up those positives and negatives, it'll always equal to 0. We don't want that. We want to know the size of the deviation and not the direction. So how do we neutralize direction? You square these dispersions, and that's exactly what we do for all these sums. So there it is, ladies and gentlemen. So starting from the bottom, this is how we quantify the total variation in y. So the question is, how do we attribute it to the regression and the error? Again, this is just a summary. So for regression, remember I showed you, we said that, you know what, this part of the variation in y is captured by the regression. So how do we quantify it? It's the difference between y hat and y bar. In other words, the regression estimate and the mean of y. And that's exactly what we did there. That is exactly there. And the same process. You got to add it up for all the observations, and then you got to square it so that the negative and positive dispersions don't cancel each other out. And this is your regression sum of squares. And then finally, How do we quantify the errors? Well, remember we said that any part that's not explained by the regression would be the errors. So the errors would represent the difference between what the actual value for y was and what the regression had estimated for y. So the error would be yi minus y hat. That's exactly what we have right there. And same thing, we have to square. We always square dispersions. Always square dispersions. So this would be your sum of squared of the errors. Now this next column is called degrees of freedom. And when you're looking at the regression, you have to specify how many independent variables were in the regression. So if it's a simple regression, there's only one independent variable, so k would equal to 1. For the errors, the degree of freedom is, rather than saying n minus 1, it's n minus k plus 1, which really works out to n minus 1 minus k. So again, you have to take into account how many independent variables there are in the regression. And then finally, for the total sum of squares, and you can think of it this way, you're just adding these up. So if you add up the regression plus the errors, it just equals to n minus 1, because then the k's would cancel out. You got a positive k here, negative k there. And then the last column, we take the mean of each of these categories. And the mean is simply the sum of squares divided by degrees of freedom. So there's nothing new in this last column. So we just take the sum of squares divided by degree of freedom. So that's the mean for the regression. And the mean for the errors, same thing. We take the sum of the squares and divide it by degrees of freedom. But ladies and gentlemen, when you do that, this will look familiar, because in a previous module, we determined that this is the framework for calculating the square of standard error of estimate. So that's what this is. And then in the for the total, when you look at the mean, again, same thing. You take the sum of squares and divide it by degrees of freedom. This too looks very familiar. That's the framework for finding the variance for y. So what's the difference between this here and this here? SEE measures the dispersion around the regression equation. Variance measures the dispersion around the mean. And you can see that right here. There's no memorization at all. Once again, SEE measures dispersion around the regression estimate. Variance measures the dispersion around the mean. So there you have it, ladies and gentlemen. That's your Anova table. Now, using Anova data, we can determine how well the model explains the variation in y. And let me just stop right there, because it's important we have the big picture before we do all this quantitative analysis. We want the model to do a good job of explaining what's happening to y. Because if it's doing a good job, then we could use it to forecast future values. So I just want to show you the motivation for using an Anova table. We're not just crunching numbers for the sake of it. We're actually seeing how significant or how strong the explanatory power is for this model. So the first thing we want to get from the Anova table is the R squared. And as we saw from a previous module, R squared is the variation of the dependent variable that's explained by the model. So this looks at variation as a percentage. So for example, if R squared is 0.58, that would mean 58% of the variation in the dependent variable is explained by the model. And therefore the remaining 42% would be explained by the errors. So of course, ladies and gentlemen, we want a higher proportion of the variation in y being explained by the model and less being explained by the errors. Now, how do we find R squared? And here's your connection to the Anova table. To get R squared, we look at the regression sum of squares and divide it by the total sum of squares. So here's the Anova table. Here's your regression sum of squares, and here's your total sum of squares. The other metric that we can compute using Anova is standard error of estimate, which is simply the square root of SEE squared. And what this does is it expresses variation in absolute terms. So, for example, if SEE is $4.70, it would imply that on average, the actual observations deviated by $4.70 from the regression estimate. So I just want to point out what's happening here, ladies and gentlemen. All these metrics, so whether it's R squared, SCE, and we'll just go a little forward a bit, FSTAT, they're all telling you the same thing. They're all telling you how significant the model is. But their format is different. R squared is telling you how significant the model is in percentage terms. SEE is telling you how significant the model is in absolute sense. And now FSTAT, let's have a look at FSTAT. FSTAT looks at the mean sum of squares of the regression and divides it by the mean sum of squares of the errors. And what this says is how much more of the variation is explained by the regression relative to the errors. So when you convert this into a ratio, which is what FSTAT is, that's a ratio, the way that the significance is being formatted is in the terms of a multiple. It becomes a multiple. Now all this information, whether it's mean sum of squares or SEE squared, it's all found in the Anova. Here it is, the Anova table. So you see SEE squared, it's all in the Anova table. And then to calculate FSTAT, remember we said we need to see the measure the mean sum of squares of the regression relative to the mean sum of squares of the errors. So all this information is available in the table. Now how do we interpret the FSTAT? Well, let's do an example. Suppose that we're told FSTAT is 18. Now we know FSTAT is mean sum of squares of the regression divided by mean sum of squares of the errors. So this equals to 18. Now, what I like to do is, whenever I'm giving a ratio, I like to flatten it out. And here's what I mean by flattening it out. So all I'm going to do is I'm going to bring this over here, and we get the following expression right there. And now it becomes very easy to interpret. Here's why. For every unit of variation explained by the errors, 18 units are explained by the regression. And there it is. Therefore, the regression explains the variation in Y 18 times more than the errors do. Now, ladies and gentlemen, remember I told you that all these metrics tell you the same thing? So now I'm going to show you how that is. I have two models here. Here's the first model, here's the second model. Now in the first model, look how close the regression, remember the regression is represented by the blue line. Look how close the regression is coming to explaining the actual observation. But now look at the second model. Look how far off the regression is. So for example, when X was here, the regression estimated Y to be there, but the actual value for Y was far off. Same thing here on the downside. When X was there, this is even worse. The model would have forecasted Y to be there, but the actual observation for Y was all the way down here. So right off the bat, before looking at any of the metrics, we can see that this here is the better model. It's the stronger model. It's more significant. And of course, this would be the weaker model. But now have a look and see how these metrics indicate whether the model is strong or weak. So first, R squared. Remember the definition of R squared? It's the percentage of the variation in Y that's explained by the model. And here the model is doing a much better job explaining the variation. So the R squared here will be high. And as a result, for the weaker model, it will be low. So now let's look at SEE. SEE is the error. The E stands for error. This E, standard error. So here, with the first model, you can see that the errors are very small. There's very little error between the regression estimate and the actual observation. So the error is low. And then over here, you can see it's high. And then finally, if you look at FSTAT, FSTAT is a multiple. It says how much more does the regression explain relative to the error. well, you could see here that there's very little error, which means the regression is doing most of the explaining. So therefore, the f-stat multiple will be high here, but it'll be very low with the weaker model.